Drones have evolved over the years to become the perfect line machine. Why are drones designed the way they are today? Why is he so efficient at moving so fast? In this video we learn about the mechanical designer's pet of the drone as well as its electronic controller sensors, intelligent algorithms, and even satellite technology. So let's start a design journey starting with a permit drone and moving on to the most modern drone. Let's start with a simple drone design. First, a single propeller design. Drones with one propeller provide enough lifting force to keep the drone flying through the air, but there is no way to control this drone. All it can say is that they can go up tickly and can come back. Another problem is that the body of this drone will rotate in the opposite direction of the propeller, which is a result of Newton's third of motion. You can see that the stator of the motor provides the necessary power to the rotor part. According to the third law, this means that the rotor must also deliver an equal amount of torque back to the stator, because the status is fixed on the body of the drone. Due to this reaction torque, the drone will have an unwanted spin. So why not use two propellers? This is certainly a possibility, and a company named 00 Robotics has made a serious effort to develop such a drone. The fewer the number of propellers, the less energy the drone will consume and the longer it can stay in the air. The main problem, however, is that it requires a high level of control accuracy and stability to manipulate the drone to fly at high speeds and pick up fast starters. We expect two popular drones to achieve good stability on day one due to the advancement of control algorithms. You can see that the two-propeller design pleases you rotated in the directions. In this way the reaction of the motor is stopped and unwanted body spin can be avoided. The three popular designs are rarely used. The main problems with this type of drone are the motor's reaction, torque, and gyroscope process. Both of these lead to unnecessary complications in design and algorithms. The next variation is the four popular drones or quadcopters that are usually H-shaped or X-shaped. Let us now understand the interesting force dynamics of quadcopters and see how they are done manually. To receive the horn, the operator only needs to ensure that the weight of the drone is perfectly balanced with the sight produced by the propeller. You can see the beautiful airfoil shape that they use to generate the popular lifting force. To achieve forward motion, the front propellers slow down and at the same time the rear propellers accelerate. Because of this there will be pitch motion. Now make all the force values equal by making the propeller speed the same. Let's say you balance the vertical component of the resulting income popular force with the weight of the drone. Despite this, there is an unbalanced horizontal force that drives the drone forward. Similar technology is used to inform the roll movement of the drone. Simply put, this movement is done by creating an equilibrium lift force in the left and right purses of the propellers. A quadcopter Kaya motion is achieved in a unique way. In the beginning of this video we learned about the effect of the motor on the drone as it reacts. To avoid such unwanted spins, quadcopter drones have one diagonal leg rotated against the other. This technique cancels the reaction torque completely. However, if you want to move or rotate the drone, you just have to make sure that it doesn't cancel the reaction torque, which you can easily achieve by reducing the speed of a diagonal leg. Reaction torque is proportionally proportional to the speed of the propeller. Finally, a net reaction torque will be generated and the drone can achieve your motion. Obviously, quadcopter drones are the most stable. They are used in almost every industry with their ability to move at high speed and take sharp turns. Now coming to the brain of the drone. Suppose a drone is suddenly hit by a gust of wind. The operator has to control and rear adjust the speed and rotation direction of each poplar in less than a second. Otherwise, the drone may crash. It is difficult for a person to control the situation by hand. It is this type of scenario where the most important part of the drone comes to the rescue, its flight controller. The flight controller can be thought of as a small intelligent pilot sitting inside and navigating the drone in any kind of difficult conditions. This enables the operator to now use simple controls like forward yourself, etc., which makes drone operation as simple as in a video game. To get this result, the flight controller needs a lot of input signals from various sensors. Welcome to the interesting world of drones. You might be surprised to know that most of the sensors in modern drones are the size of an ant. To make such small super accurate sensors means technique is used for this. It is actually a small machine with moving limbs. The most important sensors in this group are the accelerometer, gyroscope sensors, and the magnetometer. These three sensors are housed together in the IMU inertial measuring unit. INU drone is the king of sensors. It measures acceleration and rotation. In this accelerometer MAM sensor, as soon as the drone experiences a force, there is movement between the plates. It is in two places next to Egypt that money is generated. When the distance between the plates changes, how does the tax differ so that the variation of money tax can be easily converted into an electric signal? And those signals can be sent to the control for calculation. To get the acceleration in all the three directions, we will need a 3-axis accelerometer. When we include gyroscope also in units, then with force values we can measure rotation in different planes then to decide their altitude. MAM-based barometer sensor is used. Your flight controller or processor must properly use all the signals collected by these sensors to make the right decisions. However, before moving on to the processor part, how can we make sure that the signals produced by the sensor are perfectly curated? For example, noise can affect the accuracy of the sensor. There are some causes of noise, such as impacts, interference by the mechanical vibrations of the drone propeller, and magnetic interference. Modern drones use a technique called sensor fusion to overcome this problem. For example, a GPS sensor with IMU can provide altitude information of this drone. However, we can make this measurement superhit if we use reader technique in it. This is sensor fusion. Different types of sensors work together to produce more accurate measurements. With these actuated signals, we can enter the decision-making part of the drone. The control system part that includes the control logic. The control logic is the algorithm that further minimizes errors and makes decisions. One such algorithm is past and present to find the position of this Gautam drone of CalMind filter. Both the data reads it and uses its logic such as GPS navigation to go back home or in any such case, or in this case to stabilize the drone after the destructive effect of the wind. Finally, the same algorithm from which the logic is fed into the processor with gates and transistors, etc., takes smart decisions to control the speed of the BDC motors. Yes, quadcopter drones can tackle any challenging environment by smartly controlling the speed of 4 BDC motors. At present, a company called DG is one of the leading companies in the consumer drone market. They use a closer ration system to reduce errors in sensor output, and advanced flight control algorithms are used for more reliable output. Sophisticated algorithms are one of the keys to success. On the other hand, companies like Parrot Hotels and Unique do not have that much market in our consumer UAV drones as compared to DGP. These drones also do not have the refinement and fitness that comes with the DG's dress. We have already seen. The smart control of BDC motors by Calvin Filter Gautam ensures a stable and pleasant flight to the room. The required power, electronic circuits, antenna and sensors used by these BDC motors are supplied by a lithium-ion battery. The drone receives control signals from the user using normal radio frequency technology. The communication range for drones above them can be between 1 and 2 kilometers. Now an interesting question: what if the drone goes out of the cation communication range, not at fault? Modern drones use GPS and tower-based internet technology together to retrieve missing drones. The operator sets the home location in advance when starting the GPS daily scare. In this way, the lost drone can return to its home location by its own form.